Hello students, so today we are going to start digital communication. We'll discuss different aspects of digital communication, the building blocks of digital communication system. We'll go through the sampling process, which is the heart, or you can say which is the basic of digital communication. And then we will go deep into the different process which is involved for a signal to be transmitted from the transmitter to the receiver successfully. But before we go and start the digital communication, let us just recall what all we did in the analog communication process. In the analog communication process, as we had to transfer a message from, say, a point A to a point B. Here also, in the digital communication process also, you will have to transmit message from one point to the other point. During the process of transmission, there are two major problems that is encountered by the message which has to be transferred. The first thing is the message gets weaker as it goes from point A to B, that is from the transmitter to the, or you can say from the source point to the receiving point. When it travels, in the way it gets weaker or it gets corrupted. So these are the two basic parameters, or you can say these are the two basic technical aspects of communication system, technical mathematical aspects on which the communication system has to be optimized. That is the technical terms used for this is attenuation and distortion. So for the message to successfully get transferred from the source to the receiver, it has to have enough energy so that it travels the full distance. And also in the process, it has to minimize interference with noise so that it doesn't get distorted. What is the meaning of getting distorted? Say you want to say, suppose hello, and the person is getting the message welcome. So the two things are different, right? So you wanted to say hello, but the receiver gets a message which is welcome. So that is called distortion. That the message gets distorted from its original value, or you can say the message is getting corrupted. So that is it. And the first part was what? Attenuation. Attenuation means the magnitude of the signal gets lessened or weakened. It is not having enough energy to go from point A to point B, or you can say from the source to the receiver. Okay. Now, what we also saw in the analog communication system, what was the thing that we used for so that these two things, or you can say the first thing, basically the attenuation process, it is having enough energy so that it can go from the source to the receiver. The process that we used was called modulation. What we did in modulation, in the modulation, what we had to transfer a message, but we multiplied it with a carrier signal. It is like you have to go from Kolkata to Delhi. You will not go by walking, right? You will use a plane or you will use a train. So the train or the plane is your carrier. It will carry you to your destination. Same way, the original message has to be carried from its source to its destination by the carrier. In the process, we are modulating the parameters of the carrier. If you are modulating the amplitude, it is called amplitude modulation. If you are modulating the frequency, it is frequency modulation. Okay. Now let's get into the digital communication system. So, okay, just a second. So this is the overview that we are going to go through. Need of digital communication, block diagram of digital communication system, sampling theorem and process, signal reconstruction, sampling techniques, and analog pulse modulation methods. So all these we are not going to cover in the first lecture itself. So maybe we are going to cover the first two parts, that is the need of digital communication and the block diagram of digital communication. Then we will do the second two portions in the next lecture, or the three portions in the next lecture. This way we are going to get into it bit by bit, and completely we will be covering all aspects of digital communication. So first thing, that is the need of digital communication. As we just now discussed, that there are two major problems. You might be thinking that when we had analog communication, why do we need this digital communication. So the two major problems that we encountered is there in the digital communication also. But for that, you had the modulation. Here also you have modulation. And there are certain things which are, you can say, which are there in digital communication, which cannot be used in analog communication. So for the first thing is the signal reconstruction is possible in case of the digital communication system. Why is it not possible in the case of analog communication system? And what is meant by signal reconstruction? Why do we need to do signal reconstruction? So as I said, that the signal gets distorted, it gets attenuated, means it gets lessened in amplitude and it gets the shape of the signal changes. That's why we call it that the signal is distorted. So for this purpose, after every certain distance, you need a regenerator, you need a reconstructor, and that reconstructor is going to make the signal reconstruct the signal so that the same signal is received at the receiver. And if it is not the same, at least it is very less. The error is very less. That is your second thing, performance metric in terms of error. Okay, now you can say that, okay, why can't we use this thing in the analog communication? Why is it only possible in the case of digital communication? So for this, let us see the basic thing, that is analog and digital. Analog means continuous, right? Analog means continuous and digital is discrete. Digital is not actually discrete. Digital means certain fixed values, or you can say certain values, certain sample of values. In case of digital, it is only 0 and 1, but discrete means certain samples. Okay, so from discrete, we go to digital. Fine. From discrete, we go to digital. In case of digital, you have only 0 and 1. In discrete, you have certain samples. So, but in case of analog, say, for example, I say you have to choose a number between 2 to 3. Then in case of analog, the number can be anything. It can be 2.01, it can be 2.2, it can be 2.956, anything it can be. So you have a set of infinite values. But in case of discrete, you will have a set of finite values. And in case of this digital, the set is becoming even more smaller. So the set of finite signals, the set of finite number of signals is possible in case of digital communication. And so the reconstruction is possible. And so the error detection, or you can say the performance metric, can be given in terms of error probability. So let us read this part. Transmitter sends a signal from a finite set of possible signals, whereas in analog, transmitter sends one of a continuum of possible signals. So from a huge possibility of signal, anything is possible. So the reconstruction is never accurate and it is not possible. But in case of this digital, you will have finite set of values. Say if you're taking 2 to 3 also, then they will give you a step value. That is, say the step value is 0.5. So you will have only two values, 2, 2.5 and 3. Or say they told you the step value is 0.25. So you will have 2, 2.25, 2.5, 2.75, and then 3. So these are the 4 possible values. And if you are getting any value, say you wanted to get 2.25, and you have got 2.5. So from this possible set of values, you will do the reconstruction. This is the major reason why signal reconstruction is possible in digital, but not in analog. A performance metric in terms of error probability. The same thing, these 2 points are very much related. As the receiver has to make guess from a finite set of possibilities only. That's why it can tell that yes, your error is this much or your error is that much. If you don't know the range of the correct value, you cannot say the error, right? That is why the digital communication, these two things are possible. Now, the next part is long distance communication and signal cleaning is possible due to the use of signal regenerators and repeaters. At certain intervals, at every certain distance, you use signal regenerators and repeaters to reconstruct those signals. That is, if the signal is distorted in amplitude, distorted in phase, or even if the signal is getting weaker. So you can amplify those signals. So signal regenerators and repeaters are there. What are these signal regenerators and repeaters? These are analog. These are circuits. Which type of circuits? Amplifier circuits or circuits which will reconstruct your phase distortions. Those are the circuits which are there in the signal regenerators and repeaters. Now, some aspects of the need of digital communication with the point of view of, you can say, the modern usage. So everything nowadays is digital. The data is digital due to the growth of computers. In the growth of computer system, the digital data is there everywhere, and that's why the processing of digital data can be done easily by the digital communication system. The next important point is the integrated service network. Integrated means in a one system, in one platform, you can have different types of data, or you can say different type of sources can be channelized into the system. That is the voice. You have data, you have video, you have voice. These three types of sources are there, and they can be propagated in a one common format using some common infrastructure to transmit. Now, again, very, very important part, processing of digital data by digital electronics, example, processors and VLSI is cheap, reliable, and miniaturized. Okay, so digital data can be processed by digital processors. And also not only these, the processors, the DSP processors are very fast. They are very fast, and secondly, they are also reprogrammable. So the error correction is possible, and that will help you to make a robust system. The feedback mechanism gets very much boosted up when you have the facility to correct the errors. Okay, and this is because you have the lookup tables there, and those things are just reprogramming that you can redesign the processors. The processors and VLSI is DSP processors and VLSI is cheap, reliable, and miniaturized. Miniaturized means it is occupying a small area. Why is it important to occupy a small area? Now, if the thing is occupying a big area, that means a huge amount of power supply will also be needed. So all the development in VLSI is all going through the lesser and lesser use of power supply and more faster systems. So less power supply, low power supply, and fast. So that is the aspect of VLSI. We'll not go into that, but still you should know that this is the way the development is going on. And with the development in VLSI, the digital communication system is also getting familiarized, or you can say more popular. Now, transfer of information in encoded form, encrypting the signals, providing fidelity and accuracy by keeping out the interference of noise. So we have discussed from the very beginning about the interference of noise with the original message signal. You want to say hello, and the receiver has got a welcome. Why did it happen? Because of the interference of noise. So the signal has become infidel. So the accuracy of the signal is compromised. So that can be saved, or that can be protected in case if you encode it. How do you do this encoding? You have the error correcting codes, you have the redundancy bits you are putting in for encrypting the actual information, or for adding some bits, or by adding some bits you are trying to make the system unique, so that whenever at the receiver it is going, then with that uniqueness of the system can be recognized, or the signal can be recognized. Digital system allows easy implementation of error correction and detection techniques. So the same thing. Now we come to the very important part, that is the block diagram of the digital communication system. So okay, let's give a 1 second pause so that you digest all that we needed for the digital communication system. Once again, let's go through in our mind the two major problems. Let's first pause for a second. Okay, now let's think that why do we needed a digital communication system? The message has to transmit the whole distance, that is the long distance communication is possible. Message has to be correct. Correct means it has to be free of error. So it can be reconstructed in the process. and that is easily possible in case of digital communication because you have to choose from a certain set of finite values. And third very important point was that development in computer system, VLSI, use of digital electronics. So we got an overview that why do we need the digital communication system. Okay, now let us see the block diagram of digital communication system. So from the source, you go to the transmitter, to the channel, to the receiver, and finally the info is received by the user. This is the same thing that we encountered in analog communication system, but inside the transmitter and inside the receiver, the things are different for digital communication system. In case of analog communication system, inside the transmitter, you had the modulator only. But in case of this digital communication system, you have a formatter, you have a source encoder, channel encoder, and then the modulator. In the receiver, just the opposite of this, you can say. The modulator, opposite is demodulator, channel encoder, that is the channel decoder here. The source encoder, here it is the source decoder. And in this formatter, we will go through what we are having is the low pass filter. Okay. Inside the transmitter, you have this formatter. The formatter is having sampling, quantizing, and encoding. So what is the process? What is the meaning of sampling, quantizing, and encoding? Let's see this part. So when you are transferring from analog to digital, or first we'll go to the discrete portion, then we'll go to the digital. So the continuous time signal has to be transformed into a discrete time system. So the signal is having the values at all the instants, right? The analog signal is having the value at all instants of t. But in case when you want to transfer it into the digital part, you have to sample it. So for sampling it, what you will require is you will take certain instants of the signal. You will take certain instant of the signal. Say this I am taking at 0, I'm taking at t1, taking at t2, and this way I'm going on, taking at t3, then at t4. This way, I took certain samples of the signal. So say at 0, the value was 0. So at t1, the value is say 1. At here, the value is say 3. This point, it is say 5. So you took all these values, right? So what happened is, the time is discrete, but the value of the signal at these points are dependent here, and these are not completely discrete. So this is the time is discrete, the instance you are discretizing, discrete time, but the amplitude is almost continuous. At these points, those values you are taking. So discrete in time, but continuous in amplitude, you can say. And these values you take. So at the certain instance you are taking at t1, the value is say 1. At t2, the value is 3. At t3, the value is 5. So these are the samples that you are taking. Samples of the continuous signal. This is called sampling. There is a full theory there. The process of sampling, we will go through that. The Nyquist sampling theorem, that we will be doing. At what rate we should sample. Means I say that I am taking at the interval samples at the interval of 1 second. Will that be good? Should I take the samples at the interval of 2 seconds? Which is good? So all those we will study in the sampling theory. Right now, let's first complete the block diagram of the digital communication system. So the analog signal has to be converted to the discrete time systems. How do we convert the analog signal or the continuous time signal? The continuous time signal is converted into a discrete time signal by sampling. Discrete time signal by sampling, by a process called sampling. Now, after this, the second process is quantizing. So inside the formatter, inside the transmitter, you had 3 processes, or you can say basically 2 processes. Inside the transmitter, you had the sampling and quantizing. So sampling, you understood, you are converting the continuous time system into a discrete time system, a discrete time signal, a continuous time signal into a discrete time signal. So you are taking only the values of the signal at certain time instance, not all the time instance. You don't have the value of the signal at all the time instance. So after that part, we are going to quantization. What is quantization? In simple terms, or for the basic first part, you can understand that it is rounding off. We decide the number of levels and then we round off. It's not like you can round off for everything. Say suppose you have you sampled this signal. Say you sampled this full signal and you had values like at this point you had a value, say you had a value called say 6. This point you have say 6.1. This one you had say 5.9. This value at T4 you say it was 5.7. Then this value at this point it is 4.8. This value say it is 3.8. And then you have this 2.7. Now suppose I will fix two levels right now and I will have a threshold. One threshold and there is one threshold and we are putting two levels. The threshold is like what do I mean when I say threshold? So let us say if the value is greater than say 4.5, if value greater than 4.5, then I will take it as 6. Then value equal to 6. Okay. If value is greater than 4.5, lesser than 4.5, then I will take value equal to what? 4. Value equal to 4. This is just for if you are taking two levels and one threshold. The threshold for you is 4.5 and the levels are 2, 6 and 4. So see this 6 will be what? 6 will become 6 because it is greater than 4.5. 6.1 is also greater than 4.5. It will become 6. Again 5.9 is greater than 4.5. 6. 5.7 will also become 6. 4.8 will also become 6. 3.8 is going to become 4. 2.7 is going to become 4. So now the sampled signal is quantized. Okay. There is a theory of this again, quantization, how we do, but for right now, you just can understand it is rounding off to certain values. And how do we do that? We will go through the full detail in the next class. But right now you understand. Now after this, we go to the process of encoding. What is the process of encoding? In case of encoding, we change this discrete values to zeros and ones. You will only have the digital values. So when you're having certain values, not discrete values, but not 0 and 1, that we call discrete data or discrete signals. When you have only zeros and ones, train of zeros and ones, that is called the digital data. Now, so from you can take it as encoding is the transformation of discrete data into digital data or into the set of or a strain of data of zeros and ones. Now here you can see in the digital communication system block diagram that you have a source encoder and also you have a channel encoder. So what is the function of the source encoder and what is the function of this channel encoder? After the quantization process is done, the transformation into 0 and 1 is the encoding process. The source encoder, what it does is it compresses the signal. So if it finds that how to compress the signal, and without loss of information. Okay, without loss of information, how can you compress the signal? So if you have say two signals almost same but differing by a say 1 you have 1 1 1 1 0 1. Okay, and the other signal 1 1 1 1 1 0. So for this signal, if you write 0 1, these two signals can be differentiated, or you can say that this one was my signal A and this one was my signal B. You can easily understand that you are transferring, this is my A and this is my B by just these two bits. So these two bits are the very distinguishing bits or the unique bits over here. Okay. So by these two bits, you are understanding whether it is A or B. So that is the thing that here source encoder is doing. After that, we have the channel encoder. What is the work of the channel encoder? The channel encoder is, what is it doing? The source encoder was compressing it. Okay, so the source encoder is compressing it, and the channel encoder is adding redundancy bits to the signal. The channel encoder is adding redundancy bits to the signal. So what happens when you add redundancy bits to the signal? You are adding the bits for error correction and detection. So you can easily detect the error at the point of transmitting, and when you are in the receiver, that time it can be corrected by the decoder. And then we come to the modulator. You already know what is the process of modulation. Certain parameters of the carrier signal is varied according to the instantaneous value of the message signal. Say amplitude modulation, if you want, you will have a high frequency carrier signal. And then if you want to amplitude modulation, this one was your, say, original message signal. Then what is going to happen? How do you form the amplitude modulation? How will the signal look after this point? Right? So if your signal is going to look somewhat like this. The values will change according to the instantaneous value of the message signal. So the envelope will look just like the message signal. The envelope will look like the original message signal. This one is getting varied. That is the process of modulation. When you are going to the demodulator, the circuit is such that the original signal is constructed, and then you have the decoded. Again, the source decoding is done. Finally, here you have the formatter. In the formatter, you have the low pass filter. What happened is that the high frequency signals are suppressed and by the low pass filters. And also in the decoding, some interpolation is done. Some interpolation is done at this point in the formatter. Why? What is interpolation? So when you took the samples from the original signal, now you had just the samples, right? At this point, you are having just the samples of the signal. You are just having the samples of the signal over here. But now you want the full signal at the receiver. You want the complete thing. So you want the value between these 2 points. You want the value between this point and this point. So you need to interpolate. How do we interpolate? We can use any process for interpolation. You can use straight line or the method, or you can take simple mean. You can take out the value of this point. Again, you can take these 2 points and take out the middle point here. This way you will go on interpolating and reconstruct the original signal. So after demodulating, channel decoding means whatever the redundancy bit was added, from there you will find the signal. Then the source will decode the original signal, source decoder, and then they will reconstruct. The full thing will be formed at the output. This is the full process of the digital communication system, the block diagram. After this, we will be going through sampling. First, we will go through certain terminologies which are associated with the digital communication system, and then we will go into the sampling process. Thank you for today. Let's end it here.